why did the industry struggle so much to come up with a unified, efficient software stack for edge AI deployment?
Think about the efficiency of the hardware first, because that's your biggest investment in bringing a system to the market.
Do you think the hardware we have right now are good enough for edge AI, or would you think that there really needs to be a fundamental shift or rethinking in terms of where the hardware needs to go to truly unlock the AI performance that we can bring to the edge?
That's a super tough question, and I don't know whether I'm knowledgeable enough about hardware to just give a very general answer to that. So,
if you could clarify any misconception about AI performance or AI compute for our audience that is watching, which happens to be mostly developers in the edge ecosystem, what would that one thing be?
I think you shouldn't be demotivated by a specific SDK you got for your system that you're currently working on.
And this is a big problem in the industry right now is edge AI is such a new field as of now that
they do not have the resources to train a new model. They don't have the skills sometimes. And I think that's also fair. That's just how the age of technology just progresses, right? Over time, we will see more specialized models emerging, I think, as well.
Hello, everyone. Welcome to the 4th episode of Beyond the Bit. I'm your host, Saharsh. And today we have a guest who realized that you could build the most complex, most sophisticated AI models, but if you cannot get it deployed efficiently on hardware, then it's completely useless. Our guest today decided to tackle that very problem, and he is none other than Dr. Moritz Josef, CEO and founder of Roofline, who's building the next generation of sophisticated compiler infrastructure to help squeeze every drop of performance out of edge silicon. So, Moritz, welcome to the podcast.
Hello, thank you, and it's very nice to be here today. I'm excited for the podcast discussion today.
Awesome. So, why don't we start with Dr. Moritz, a little bit about your background, what you did before starting Roofline, and what is the origin story for Roofline? How did it come to be?
Yes, at Roofline, we are building, as you said, a company that really wants to bring AI models to different chips much faster than it is possible today. And that's also very much motivated from my background. So I'm coming more from the computer architecture field. I've always worked in the intersection between hardware and software. So always working on this very interface to bring different models and different software tools onto new chips. And so I'm actually having a research background. So I worked also on emerging memory technologies previously. And then in this research field, we saw that there's a huge need for software infrastructure, but also in existing NPUs, GPUs, and CPUs at the time or today. All these three systems are still struggling with software support to a various degree. And this is what we are trying to solve at Roofline. And this is also just very much in line with what I've done previously in that regard.
Okay, awesome. But let's take a step back. Why do you think we ended up in this place in the first place? Why did the industry struggle so much to come up with a unified, efficient software stack for edge AI deployment?
Yeah. So I think it's really down to the conundrum that in the edge AI deployment, efficiency is king. So you really have to think about efficiency first, and what this yields is a development process where you very often think about the efficiency of the hardware first, because that's your biggest investment in bringing a system to the market. And with this huge challenge, what you are building is basically always a pretty much over-optimized solution for a specific use case that you're thinking about at the beginning. And to be very honest, I think that's just supernatural. That's just how you would build a system, because you have a specific challenge from your user or your target market in mind, and you're solving for this and you're optimizing for this because you want to meet the specific performance and power constraints in your edge AI device. And once you release it to the mass market, then you might be in the situation that you actually want to deploy models that are also broader to these devices. And in that regard, then you get a generalization problem for your deployment solution, because it might work for specific models, but it might not generalize in that way that you're actually looking for it. And so yeah, that's why I think it's just honestly a pretty natural way how the industry evolved from this efficiency constraint. And then solving this now is probably a very daring challenge, but also from our customers, we always get the feedback that it's really one of the key challenges for them once they want to really move from a smaller deployment to mass market and production-ready deployment for their systems.
I see. I mean, that makes perfect sense. But this is something that we touched on in one of our previous episodes as well. And do you think that there's a bit of intentionality behind this, in the sense that the legacy silicon players are purposely building tool chains that are very specific to their products, maybe a little bit fragmented on purpose, so that the switching cost remains high for users, so that once they start using one platform, they're sort of bought into it. They're stuck so deep within it that switching to another one, just the thought of them scares them because of the amount of resources, time, cost involvement in doing that.
Yeah, that's I think is a pretty good question. I think it really depends on the specific strategy. So obviously we have companies that are very much taking this walled garden approach to their hardware and software systems. So I think there are companies out there that are in this specific bucket. But I wouldn't generalize it to like all legacy semiconductor companies. So we also see a lot of interest in these ecosystem approach, especially from larger semiconductor companies that are working with us. And I think it's really down to the realization that if you look at the history of the edge AI market, that a lot of these companies have tried to build a more siloed solution because that's just the need, as I just tried to explain, from their technical development process. And once they are there, they really see that unlocking the synergies from an ecosystem just gives them a broader adoption of their chips. So I think on the contrary, a lot of these players now see the value in opening up in this ecosystem plays, and that's also, I think, reflected on the different strategies you see from bigger semicon companies also trying to push more into this ecosystem way of approaching developers.
Right. Yeah, I think that's especially true because everyone in the industry is realizing that technology is a great equalizer, and maybe not today, but tomorrow or sometime in the future, all of these walled gardens will be broken down when AI makes it very easy for everyone to create software, maybe even create tool chains that can bridge the gap between different specific architectures. So then if this is out of the question, let's say, then it sort of leaves us with another thought, which we've also seen in our experience, is that when data scientists develop models, they are not really concerned with hardware at all. Like most of the times, they don't really think about where the models will be deployed, what they'll be used for. They almost create the models in isolation in PyTorch, TensorFlow, whatever the development environment is. And then, that problem gets transferred to someone else, maybe the embedded engineer, to figure out how to optimize it. So it's partly also that data scientists are just not thinking about the hardware constraints at all. Do you agree? Do you also see this in your work as well?
Yeah. So I think that's probably true just from the nature of the typical developer flow that you see in like AI product companies, where there's also often different people and different responsibilities in these roles. What we also see is just like if you take a look at the typical PyTorch models, there's some I don't know, Python code jacked into the middle of a PyTorch model, and you somehow have to deal with it from a deployment perspective. So I think there are a lot of challenges in that regard. What we are working on at Roofline is to lower this barrier generally, so that the developers can still innovate at the speed they want. Because I think key of this not thinking about hardware is also that they have the opportunity to just innovate pretty raw, right? They just can think about very nut models and just say, okay, I just go for that because it should somehow work. And honestly, I feel this need from the developer side, and I think to a certain degree we should try to address it. And that's what we are trying at Roofline, to build an as generic, as coverage focused compiler, to really being able to get the AI developers at their speed, at their specific innovation ideas, and then trying to build a path that is more scalable so that we can bring as many of these models and these ideas onto different edge AI systems as possible. But yeah, I think generally a little bit more education about how edge hardware works, I think, and also the specific constraints probably would be pretty helpful in general. But I think that's also just a wish that we can have for, and it's too difficult to address.
I think you said it beautifully. Is ideally data scientists should never have to think about this problem, and that's, I guess, what Roofline is exactly working on, is like give data scientists the freedom and the ability to truly innovate, build advanced, sophisticated AI models, and let your toolchain, let's say, take care of the next part or the last mile of the deployment. So maybe you can tell us a little bit more about how exactly Roofline works as a product. What does it really do in terms of model compilation? Because now we're in a situation where there's not just MCU cores or general CPU cores. There's a mix of CPUs, GPUs, NPUs, all kinds of different kinds of compute cores mixed together often. So how does Roofline really deal with this fragmented deployment?
Yeah, that's true. So if you just take a look at the market, you see that in the last years there have been released a lot of heterogeneous platforms. So that means SoCs, so systems that comprise CPU cores, sometimes even heterogeneous CPU cores of different sizes. You often have embedded GPUs on these systems, and then you also have dedicated NPUs, and then again sometimes multiple NPUs tailored towards specific use cases, for instance, different power and performance envelopes. And in these systems, the deployment challenge is pretty tough, because what you need is a deployment solution that can cope with this heterogeneity. So you need interfaces to talk from one software solution with all these different components. And then you also need a compiler solution or a deployment solution that is able to generate code for all these different kind of devices on your system. And so this is what we are doing at Roofline. So what we have built on top of MLIR and ERI, so utilizing as much open source infrastructure as is out there, is a deployment solution, a SDK in that regard, that can take any AI model and then bring it to these different heterogeneous SoCs. And so what does it mean specifically? It means that you can take a PyTorch model, a TensorFlow model, or even an ONNX model. So really, we try to be independent of the framework. And then also it can be very different model architectures. So we are looking all from conventional image networks down to transformers. We are looking at all these different model architectures and then abstracting them mathematically to then generate kernels for the different targets from these mathematical abstractions. And here, the secret sauce really lies in modularity. So really lies in the way how we abstract the model through different intermediate representations. You can think about it as languages in a regard to translate it from one language to the other, and then always have a clear optimization path on that. And this allows us to do basically two things. One is it allows us to retarget the code, so to bring it to these different devices from one unified toolchain. And the second thing that it allows us is to hit very good performance by utilizing optimizations that are already out there, but also specific optimizations for a GPU or an NPU that we get from our customers, so that it still is aware of what hardware optimizations have been built. So it does not throw away all the effort that has gone into the specific optimizations, but it tries to reuse them as much as possible.
Got it. So, let me see for the benefit of our audience if I got this right. So what you're saying is that at the top layer here, you have your TensorFlow, PyTorch, whatever language the model is written in. Then the next layer would be something like an ONNX, maybe, like an open neural network exchange format, then MLIR, and then maybe the hardware specific architecture, whether it's a GPU, NPU, CPU. Is that sort of how you're saying it works? So that
Yes.
Even if you swap out the hardware at the bottom layer, you don't really have to do everything from scratch. The top three layers are the same, and then you just figure out the MLIR to some different kind of hardware architecture that you have to do.
Yeah, obviously the devil's in the details, but that's precisely what we are doing. So we are taking the AI model from a very abstract general definition of it. We are bringing it then through these different representations so that you can branch off at one point and go to, for instance, your NPU toolchain or your GPU toolchain, just as you said. And we think that MLIR as a technology is extremely powerful to do this. It has been around for 10 years now, and it is basically adopted by every major player in this field. I think everybody honestly uses it, to be very frank about it. So it really isn't like, it gives the infrastructure to build ecosystems on top of that, because if everybody's using similar languages to describe their hardware features and similar optimization paths, then it really gives us this inflection point where we can now build a unified software infrastructure on top of that.
Got it. Awesome. And is your tool mostly being used by large semiconductor companies? Are they your customers, or do you also see some end users like OEMs, developers, engineers actually working on the product who ask to use your tool so that they can keep their models proprietary and be able to use it across different architectures? Who's really the customer or end user for you?
So it's actually both at this point in time. So we have a very strong footprint in the semicon space, where we are directly giving our tools to different semiconductor companies that use it as a deployment solution. for the specific SoCs. But this is very much also driven by their customers' demand. And so we also interact with end customers. And there's something just from the company timeline, we are now also increasing our footprint in the end user space even more, because it's a little bit a chicken egg problem, right? You need to support like a critical mass of systems to actually have value add for the end customer. So we first went into more the semiconductor space, solved specific problems there, and are now also working on specific solutions, for instance, for OEMs in like first scenarios to really deploy this. So also in the next months, you will see more and more case studies from us being released, where we are also showing how we address specific end user use cases that they bring to us, and how it also enables you to migrate, for instance, from like a Jetson board to one of our customers' boards, for instance. This is the typical cases that we see at the moment.
Yeah, and I would imagine that that really would be very interesting for some of the large OEMs who spend a lot of time, let's say, developing proprietary models, and they don't really want to, give it to semiconductor companies to then translate it for them. They want to hold on to it, keep the ownership and the IP private. So that really helps. And I would imagine that even from a semiconductor ecosystem perspective, it probably helps you, considering that the ARM or RISC-V architecture is still the most prevalent architecture out there, and it's being used across so many different processors, SoCs, and so on, right?
Yeah, that is exactly how it goes. So we are pretty happy that there's a lot of ARM and RISC-V general exposure, because we need to somehow run our models on the different target devices. And for this, so we have developed a small runtime that runs on a CPU core, and that typically is like an ARM or RISC-V core, and then also we can just test it internally. So having some standardization in that regard for the ISA on the CPU side really helps us to get going. And then also on the CPU side, we can use our tools to also heterogeneously execute models on CPU plus another device at the same time. So one typical case we see for that is that you have an NPU that is very efficient in specific operations, but does not support like everything that your model brings. And that's fully fine, because you don't need to, right? You need to optimize the 80 to 90% operations that you have on your device. And then if there's like 10% of operations that are not super effective, but they just run on the CPU, that's fine for a lot of use cases. And so this is something that is very much enabled by our toolchain. And then we rely, for instance, on for ARM, for instance, we're also collaborating with ARM and using their LLVM compiler solutions that they have for their systems. And this is really enabled by this ecosystem in the semiconductor space.
Awesome. That's amazing to hear. So, now let's say if we talk a little bit about the use cases side of it. So, of course, you're not involved in the model optimization and you're focused more on the deployment and making it possible to run it efficiently on edge hardware. But from your experience working with users, developers, what are some of the most common challenges you see where, someone developed a model that was running in the cloud or some other larger environment, and suddenly they asked to deploy it on a small edge silicon, and then they see that, now the power consumption is not within the power budget that they wanted, or the latency is maybe a little too high, or the model just doesn't fit within the memory profile. What are some of the most common challenges that you're seeing?
Yeah, I think it's honestly challenges across the board. So it is from like optimizing your quantization to fit to your system, to making the model smaller in terms of like model distillation. It is also around just generally getting it running, because you might have in the cloud operations optimizations that run that are also within the like memory constraints that you have in your system. You can get the operators in, you don't hit the memory wall there yet, and on the edge system you actually do, because you do not have enough resources on your bus, or just not enough transfer speed between memory and CPU cores. So it's challenges across the board. And I think also this is what you currently see in the startup space. You just see a lot of companies on all these different layers, from the cloud model down to the actual edge device popping up. So from like companies specializing on quantization, making models smaller, pruning, sparsity, getting everything running, and then at the end, like deployment layers like us. So I think there's just like a huge range of different approaches you see. From our specific deployment perspective, we see the most daring challenge for customers that we talk to from just purely deployment is actually that they did some optimization. They think it might actually run on the target hardware because, I don't know, it's like small enough in terms of memory footprint, and then it just doesn't work. So they have thought about specific optimizations, but it does not run through the default SDK they get for their target platform. What do they have to do? They have to think about, okay, I have to do the same thing again, actually revalidate the model just in a way that it fits my target hardware that I selected myself or got selected by the organization that I'm working in, right? And so this is the core challenge that we are seeing, which is really around, having incompatible models that should fit in generally, but they actually don't run in practice on the target hardware.
This is very interesting. This is an interesting insight that you bring forward. I wouldn't have expected this. So essentially, you're saying that just getting the model to run on the target hardware is difficult enough that the question of optimizing for power and latency and all these things sort of takes a backseat. Like getting it run is a big enough problem that first we solve that, and then maybe engineers start to think about, okay, now we have it working. Now maybe we start to fine tune and see the best we can do.
Yeah, maybe maybe I didn't really bring my point. I think it's not on the backseat. I think it's like going hand in hand. Honestly, I think often these model optimizations are step one that has been taken, right? It's already been done. You already have an optimized model, and then you realize it actually doesn't work, right? So think about a typical use case where you run it still in the cloud because you think, okay, I have, 10 gigabytes of memory on my target system. So if it runs on the cloud with a 10 gigabyte of memory limit, I'm fine. But you actually aren't. So you optimize your model. You think you have done it, you have achieved it, and then you want to deploy it to the target system. And then what we see is that there are a lot of ambitious projects that try to bring something on the edge AI device. They tested it in the cloud, they built their POC, they show it to management. Management is like, oh, cool, let's try it as a product. Then they are, okay, I'll just buy a specific board, and then we build a demo for fair, right? And then it just breaks because they can't deploy it easily. And then there's so much friction that the product is never released. And that's, I think, just in the overall process, it's a very daring challenge. And this is also why we are trying to solve it.
I see. So I guess what you're saying is that users do try to optimize it, but they're often not aware of the full range of constraints that they have to work with. So when it gets deployed, there comes like the sticker shock is, okay, it still doesn't really work. Yeah. But in everything you said, I picked up on something very interesting. You said that there's not enough memory or not enough transfer speed. So we hear people often obsessing with a lot of metrics and benchmarks, like the number of TOPS a processor has, or the number of the amount of AI performance the target hardware has. But it's not really about that, is it? It ultimately all comes down to the memory that the models can be accommodated in, and then basically the data movement bottleneck, because that's essentially what determines whether AI models will work well or not. Is that correct?
So I think it's to a certain degree it's both. So you need to hit this like a certain amount of TOPS to just be able to run it, right? But then what does TOPS mean? I think it's really dependent on the target system you're talking about. And this is very much determined by memory constraints, as you said. So I do fully agree on that. So you might have a system that has a mathematical number of n TOPS, and effectively, if you do it well, it runs at like a higher speed than your typical other competing products at n TOPS, right? So you might actually be able to squeeze out more performance just because you have better memory bandwidth to your specific product, or because you have very well integrated it with your memory system of the overall system that you have. And this is also what we see with our customers, and the specific architectures are obviously all very confidential, so I can't talk about it. But we see that if companies invest time and effort into well aligning the memory hierarchy with their compute that they have, that they typically get much better results in terms of running larger models, having better latency, and also the power consumption drop. So I think optimizations in the memory space are very critical today. And so also with new emerging memory technology, I think we'll be just getting an even more multidimensional problem, where you don't only think about the bandwidth to your device, or do I need a certain number of memory, but also which kind of technology fits my needs best, and where do I integrate it in my overall memory hierarchy.
This brings us to a very interesting segue, because I know that in your former life, you happen to have done some research on neuromorphic computing and neuromorphic hardware as well. So where do you think this balance of optimization lies between hardware and software? Because right now, Roofline is sort of working on making sure that the software is optimized as much as possible. AI models take advantage of the underlying hardware, which is fixed, as much as possible. But how much work do you think needs to be done on the hardware end to sort of meet in the middle and then be able to deliver the kind of AI performance that the edge really needs?
So I think it's very typical that you need to invest a lot of effort and resources into a good hardware, because otherwise, even the best software cannot squeeze out more performance than there is, right? So if you build a system that, for instance, talking about memory, has a very a very disadvantaged memory hierarchy or something where you need a lot of time to just get data in and out of your main memory, then this is something that will limit your performance. So we can't solve that problem. Our software can be as good as you can imaginarily think about it. It will not solve the core limitations your system imposes. So I think it's really down to making sure that your hardware is well designed, and all the hardware engineers that we are working with are super aware about this challenge and are extremely cautious about how to build their systems and which kind of memory to use and where to employ it. And then on top of that, I think once you have built a good system, then you can't understate how important software gets, because once you release it, then it really is more a software problem. And it gets, like, in the life cycle of your system, it gets even more software over the time of your system living, because you have new models that customers want to deploy, for instance, to a system that is already out there. And they say, hey, it should also retrofit onto something I bought 5 years ago. Is it possible to run it on an older chip or something like that? So the longer you're in your life cycle, the more the software optimization play a role. And I think that's just pretty much the very natural cycle of the EDA kind of flow. So you really have to think about how to build your system well at the beginning. And then once you transition to deploying it to ever larger kind of audiences and having it also in the market for a longer time, then it gets more and more software challenge.
Absolutely. And I see, of course, Roofline is one of the very important players that's doing all you can to help tackle the software optimization parts. And I see more and more companies building tool chains for AI model generation to embedded code generation to help tackle down this problem. But if we come back to the hardware a little bit, do you think the hardware we have right now, or more specifically the instruction sets that are being used by chips right now, are good enough for edge AI, or would you think that there really needs to be a fundamental shift or rethinking in terms of where the hardware needs to go to truly unlock the AI performance that we can bring to the edge?
So that's a super tough question, and I don't know whether I'm knowledgeable enough about hardware to just give a very general answer to that. So I think it is, so what we see with RISC-V, for instance, is that we have this modularity in the instruction set architecture, and I think that gives room for innovation in that regard. That I think is pretty cool. So something where we see that you can, for instance, have your specific implementation of your vector extension for RISC-V, but also now with metrics extensions that we are discussing about, we see it has not fully converged there yet. So there's just more room to innovate. So I think this flexibility in the RISC-V ecosystem is just something that is pretty much welcome by the overall industry, because it just allows you to have a more flexible approach to building your hardware. And then talking about neuromorphic and non-neuromorphic hardware. So yes, I've worked in research with neuromorphic hardware, especially resistive RAM. But I think I'm just not knowledgeable enough about the current production ready deployment. So what we saw in research was there's just a huge amount of hardware challenges to actually get it running, to make it work as a technology. But I think once you have made it work as a technology, then you really have to think about, do we design it in a conventional way that it just fits the conventional way of thinking about architectures and computers in a way. I think that absolutely makes sense to have this path on the one hand side, because you want to make sure that it just is a smooth transition from your legacy systems to newer technology that you bring into the market. But then also in terms of, if you want to think about a new programming model, a new way of using them in a more neuromorphic sense, I think that's something that everybody's hyped about, and I'm just curious to see where it leads in the next years.
Yeah, I mean, as people say, the popular saying is doing hardware is very hard, because there's just such a long gestation cycle. There's tape outs, and then things go wrong, and then it's very expensive to get it out as well. So no one really knows where hardware will go. We'll just have to wait a few years to see how things evolve and what are some of the other popular architectures that come out in the coming years. But coming back again to the software piece of it, I'm sure you're also seeing in your work that every day model sizes are getting larger and larger. There's the next big LLM that's coming out. Transformer architectures are now moving to the edge as well. So do you think, from your vantage point, in the next few years, we'll be able to move these kinds of general purpose LLMs down to the edge, or ultimately it'll be the hyper specialized fine-tuned models built purpose built for the edge that will win over these very large general purpose LLM type models?
So yeah, I think it's both in a way. So what we see from like the use cases customers bring to us is that it's typically smaller variants of these large models that run in the cloud that they try to run first. And I think that just makes sense because they are well trained. They can reuse a lot of this open source models also that are out there. So like the typical customer use case we get is they either download a like open source model from Hugging Face and just want to make it run and just go from there in their first initial phases. Or what we also see is that they collaborate with specific model providers and then have closed source variants of like these larger models that are then more suitable for like smaller systems to deploy to. So I think it's really down to distilling these larger models into smaller ones at the moment. And then on top of that, we also see highly specialized models that are being used for specific use cases, but from our customer exposure, but that's like a niche thing. It's very biased what we see. It is in the language model space still niche, to be honest. So we see this in like the conventional CNN and RNN space where like the knowledge how to build these models is just much more proliferated, I think. So it is easier to build your specialized custom model. In the LLM space, we just see more companies or customers from ours that are still using off-the-shelf models to a certain degree, just because also I think they do not have the resources to train a new model. They don't have the skills sometimes. And I think that's also fair. That's just how like the age of technology just progresses, right? Over time, we will see more specialized models emerging, I think, as well.
Yeah, and this is a big problem in the industry right now is edge AI is such a new field as of now that the right kind of profiles, talent-based skill set doesn't quite exist. So even we see data scientists, model developers often taking something off the shelf, then just trying to optimize a little bit, hack it a little bit to make it work somehow for the edge. But I almost feel like in the next coming years, we'll see a new role come out of nowhere. It'll be the edge data scientist that really has, the mathematical understanding of how feature extraction works from data, how to sort of build like the right kind of models that do just enough compute to give you the kind of accuracy. And then models will get more and more specialized. But like you said, there will always be a bit of balance because some companies may not want to invest so much in R&D for data science, and some where the model really makes a difference will give them the competitive edge will want to do that.
Yeah, true. And I think also, since we talked about it earlier, in these more specialized roles that will emerge, it is probably also down to knowing what the hardware can do efficiently and what it cannot do efficiently, because that's also very different. And I think if you take a look at what happens in the cloud space, even the super large models are constrained to what the cloud hardware can do efficiently, right? So you can also not just run a random neuromorphic model in the cloud at the moment, even if you would like to a certain degree. You're also limited by just the ISAs or the architectures you have there. So I think this knowledge about the intersection between hardware and software just gets more important over time, especially in the edge case where you just need to optimize more and further.
Yeah, absolutely. Absolutely. So, now we'll sort of get towards the tail end of our episode today. And here we give our guests the opportunity to sort of philosophize a little bit and tell us their predictions and their opinions on where they see the industry heading towards in the next 5 years, 10 years, and so on. So what do you think will be the major forces, major variables that will impact the edge AI industry, both from a compute, hardware, software perspective, and how those changes will come to be?
Yeah. So I think what we see with our customers is that it's a very software-driven problem to advance the industry. So what we see is that the innovation cycles of hardware and software are somewhat disjunct at the moment. And as you already said, building hardware is pretty difficult. So you have to stick to slower innovation cycles just by the nature of manufacturing stuff that you don't have to do in software, right? So I think one of the key challenges for the next 10 years will be around aligning this to a better degree than it is currently happening in the edge AI space, so that you have the opportunity for software innovations to be just proliferated faster also across edge AI hardware. So I think this is one of the key challenges on the software side. And then on top of that, I think this challenge will just get more difficult over time because you will see even more heterogeneous architectures in the edge AI space. And this is, I think, driven by on the one hand side, like really deep technical innovations on the manufacturing technology level, on the memory side, and also a little bit on the compute side, so that you have these new kind of technologies coming in that fundamentally offer new opportunities in terms of optimization. Then you have to bring them into your computer architectures, and this will be something that I think solves specific models, specific problems, but again, not generalizing everything probably. And so you will realize that at the end of the day, the systems will just get more heterogeneous, a little bit more difficult to use. So having good instructions for developers, how to utilize these resources, which kind of hardware to employ and which kind of use case. I think this is one of the core challenges of the next 5 to 10 years, going ahead and thinking about these very different kind of systems that we will see in all kind of different scenarios employed.
So, that again brings up an interesting point. Is right now you see that beyond a certain level of workloads, GPUs basically dominate the compute hardware space as well. So going forward as well, I heard you mention heterogeneous hardwares a lot of times. So it's safe for me to assume that you believe that in the future, there won't be a similar winner takes all type of market. There will be a bunch of different heterogeneous hardware architectures or different kinds of use cases where, specialization makes more sense than being more general purpose. Is that correct?
I think so. My personal prediction is that we will see in the next years in the agile market first a wave of proliferation of just general NPUs. So basically having something like a GPU but more agile focused in a way. So I think the NPU proliferation will dominate for the next years. And by the nature of how NPUs developed in the last years, which was just more fragmented than in the GPU space, where we only have a few number of players, if you even want to call the low number a few, then I think what we will see is just like in the NPU space, just more different kind of architectures employed. And also we see that these different NPUs that we interact with just have different strengths and also some like shortcomings. And so I think in the agile space, we will see a higher fragmentation. And so having a unified software stack for that is just helping developers to just select the specific differentiating hardware for their use case, just buy it and then get going from there. Because I think from a hardware company perspective, you want to differentiate on what you are best at building, the best hardware for your specific use case you're addressing. And I think this gives a huge opportunity for just a more diverse set of hardware that just addresses all the more diverse kind of challenges that we see in the agile space.
Yeah, and I couldn't agree more with you, because at Ambient Scientific, we've sort of done the same thing, is we've differentiated our hardware to focus specifically on low power AI compute, where we can do very good AI compute, but our core value proposition is how efficiently we can do it. So that sort of lends itself very well to smaller edge devices that run on batteries, or there's power constraints, drones and robotics, which again, there are some power constraints. So no, I completely tend to agree with you on this. So, now I want to move on to the heavy hitting question that makes all the guests on my podcast smile, and they think about it and they answer. So if we think about AGI, or artificial general intelligence, it's a often talked about buzzword that no one quite knows exactly what it means, but I'm going to ask the question anyway. Do you think scaling still is the solution to achieve AGI from your perspective, or we're fundamentally missing, the secret sauce or a piece of the puzzle that will help us achieve AGI in the future?
Yeah. That's a really good question. And I get why everybody is struggling to answer that, because I think we don't know yet fully to a certain degree. I was at Europe's conference in December last year, and I really liked the way how science looks at it from two different angles. And I think one is just trying to understand how to build software that is more generalizing, and by that approaching it in a way that we don't know yet whether it will be, if something missing or something's not missing, right? We really don't know yet. So we have to try the missing pieces and see if they click. And then on the other hand, what I really liked is also observing how our existing systems are already abstracting problems and trying to learn from them in a way. So I think it's really like this two sides of the coin. So on the one hand side, developing new strategies, new abstractions, new ways of working with these systems, and then seeing if there are still gaps missing. But then also on the other hand, really understanding what we have already achieved and how these systems abstract knowledge, how these systems in a way think, and seeing that as like a separate branch of thinking and trying to understand it as what do these models do and how can we learn from their way of approaching problem solutions.
Okay. I really like how you gave a very scientific answer to this, is that we just don't know. There is not a yes or no, but the answer is we just don't know, and we'll find out more and more as we go into the future. So now,
Yeah,
I
I
think I'm
think
going to
that's
leave
like
you.
how it goes. So yeah,
Yeah.
sorry.
So I think now I'm going to leave you one last question, which is, if you could clarify any misconception about AI performance or AI compute for our audience that is watching, which happens to be mostly developers in the edge ecosystem, what would that one thing be?
I think you shouldn't be demotivated by a specific SDK you got for your system that you're currently working on and thinking, oh my God, it just doesn't work. What should I do? So don't be too demotivated by that. We're really working on finding a solution that gives you a smoother path to this development, but it's a tough problem because it's such a heterogeneous market. And I think that's also the key challenge. If you're approaching these fragmented systems that are needed for like running optimally, then you have to have some specialized knowledge about the target platform you're working on. And probably there will never be a way to just not think about the specific of your solution. So just don't be demotivated by it. Dig into the details, have the courage to understand them, let the LLMs guide you, because I think they help you along a lot of the way already. And then also, I think better solutions will emerge in the next year. So what I see in the background is just that there's a real huge push for better software in this space. And I think this will just make the life of developers much easier.
Okay, there you go, guys. You heard it from Dr. Moritz himself. Don't give up on Edge AI. And if you're feeling completely stuck, then Roofline is here to the rescue as well. So thank you so much, Dr. Moritz, for coming on today's episode. We really appreciate your time. All the best for Roofline's future progress, and we hope to see you back on the show sometime.
It would be very nice. Thank you for your time today and have a good day.
Thank you.